Okay, see, in the earlier lectures we have learned about how to describe a spectrum, how to describe an irregular sea by means of a spectrum, and how to get motions in the spectrum. So, I was having this for defining okay. We are going to revisit this part in this lecture again, because when the spectrum that we defined earlier had certain limitation, certain approximation that we did not explicitly set. What did I do for this spectrum? See, I said this record is sum of okay. What we said is, see, in defining an irregular record, we said that it can be composed of adding sine waves, but what we probably did not emphasize at that time is that all of them we assumed to have been travelling in the same direction, okay, which basically means if I add all of these things, see, eta I obtained by making something like a, I cos say k I x minus omega I t plus beta I, all of them are travelling along plus x direction, all right. Then what happened? If you stand, supposing I was standing here, I was standing here, and I look my left and right side, what will I see? I will find the crest to be infinitely long. In other words, this wave would appear like with the long lines, like if I were to draw, the wave would appear all the crest lines are long if I stand here, because it is infinitely long, because I have assumed all of them are going to the x direction. So, what happened? Take any y value, whatever the y value is, the eta is same. That means, if I were to like use a x, y, z coordinate, this was in an x, z plane, which means whatever y equal to constant I cut a plane, my velocities are all in xz plane, which means if I were to see the particle, the way it moves, etc., the velocity vector, v vector, it is all having only a dimension of or dependence on x and z. So, this is essentially a two dimensional fluid motion, there is no motion in the z direction. So, this C, that what we have obtained, this S omega, was actually what was called a two dimensional spectrum, because what we have presumed is that the waves are all going in one direction, therefore, the motion is two dimensional. So, this is what we have got, or this is sometimes called as long crested sea. However, now why we are revisiting it is because suppose you actually go on an ocean, and suppose you actually like go on a ship or make an observation, you are standing here, you are not going to see your right hand side, left hand side waves to be same. You will find out a randomness in not only in along x direction, also along y direction. So, you are not going to find this crest line to be same both sides, okay. So, obviously, somebody may question that the spectrum that I defined, okay, it is good, it represents this signal by means of sine, but what you have said is the waves are long crested, whereas in reality they are not so. So, therefore, we need to now define what is called short crested sea. Now, I will come back to this question again, see what has happened. Let us take it this is an example. Somebody went to an ocean, there is a buoy there or some equipment you measure, and the data, as I say, looks something like that. Now, it was our question, we presumed, we kind of composed that by making them sine waves in one direction. What if I were to add, we had to think that this is not only all the waves coming in one direction, but all one direction of different length, but also I think that this can be broken down to waves of all lengths in one direction and all directions. For example, now if I look, see, now I will come slowly. Now eta looks like A cos kx minus omega t. Now this is in x direction. Supposing the wave was going in x dash direction, what would be the formula? Formula would be A equal to A cos k x dash minus omega t. Okay. Suppose, see, this is when the ship is going in along x direction, and let me call this to be x dash. If not ship, sorry, a wave, this represents a wave travelling in positive x direction. Suppose I want to find out an equation of a wave travelling in positive x dash direction. All I have to do is to write x as x dash. Now suppose this is theta, then what is x dash? X dash is, it is y, x cos theta plus y sin theta. That is a standard transformation. So I can write this A cos k so this would be sorry, no, this full thing I can put. So this would be a wave travelling along a direction making theta with positive x axis. Okay. So this one. Now what we will do is that we can presume this wave to be composed of all waves coming from not only all frequencies, that means omega or k, but also from all thetas. So in other words, what we are going to think that in this point, say if I were to draw a circle, waves here that I measured are not only coming from theta equal to 0 all, but also coming from theta equal to theta, etc., etc. So what happened, then I can tell eta to be, see, earlier I had this, I will write it this way, okay, A I omega, let me write it this broad way, k, well, x, I will just write it blank here, minus something like that. See, I did not fill up the gaps. Remember what we had earlier, if all the waves are assumed to be coming along x direction, I have A I omega cos kx minus omega t plus beta, kx minus omega t, okay, this is okay. But now what we are going to do, we are going to, suppose I presume that, look, this particular thing can be broken down to all waves not only from all omegas but also from all theta. So therefore I have to put one more this here. So this, let us see, this I index is for omega. So I have to put another index theta here, and I can put j here, then this is cos theta plus y sin theta, this becomes of course also ij. Okay. So this basically represents therefore as if I am saying that the waves are coming from all directions and all some. So it's a very interesting thing. It's a question of only breaking it down. Remember that when you are sitting in an office, a satellite has measured ocean height data, and it only gives you this data, t versus eta, that is all. It is up to us to think this eta is composed of what kind of summation of waves. Now remember that we could sum all the sine waves, because sine wave summing gives a realistic wave, because waves are linear. If I put a black box, I add all the sines, then what I get is a sine wave. But here I did not say, I only added only those signs which are along the x axis, but now I want to say that look, I can break it down by adding all the signs not only along same x, but also along all x's. Okay. Obviously, that would give me a simulation of this. This picture is not going to look like a long crested anymore, because obviously there is a dependence on y. In other words, if I were to find out eta at some x and some y, they are not going to be same. Earlier there was no y, so no matter what y you took, eta was same, but now you are going to be different. So it will have a spread 3-dimensional picture. So that will be a better model for a 3D spectrum, 3D waves. 3D wave meaning, again when I say the word 3D waves, which means the velocity of the particles would have both u, v and w. Earlier I had only u and w, that means particles are moving along x axis or z axis. If you make a cut y, same, but here it is not going to be same. So this obviously is a 3-dimensional waves. So this is what is called short crested C. You see, that means if I were to break it down to this way, and now I plot similarly, you know, that process I will come energy etc., because you know the energy is the principal thing. After all, what I have to do is to plot this A. See here, what was happening here is that earlier A was a function of only theta, and now A is going to be a function of omega. Now A is going to be a function of omega and theta. That is, where is this picture? Did I do that? Okay, we can just do it from here also. See this A is going to be a function of, remember earlier it was only a function of omega in the 2D case, but now it is a function of omega as well as theta. So having said that, so the here, as I said, this is already there here, see omega and theta. Question is now I need a spectrum. Obviously what would happen if I were to put a spectrum here in this, we will come to the spectrum shape here. Once again I have to keep drawing this, you know, all the time. Say we will call it this way and this is theta. So if I were to now plot all the waves of between this frequency and this length, see now earlier what I did in a spectrum, I plotted the energy of all the waves, a quantity proportional to energy of all the waves coming between this frequency band. Let us say all the waves of energy between 50 to 60 meter I plotted one place, 60 to 70 meter I plotted another place, like that I plotted. But now what I have to do is to plot a 2D plot. So it is going to be a bell shaped curve, it is going to be a shape, it is not going to be a 2D part. What I have to do is to plot, see in this diagram, so if I call this to be, say this is theta, this is omega, then all the waves of length between this d omega, that is this omega, and angle between this is what I am going to plot here on the top. So if I keep plotting like that, then I will end up getting a graph like that. In fact, instead of doing that, we can also, this is a bell shape one, I can also do more. I put omega here and I put theta here. So what is happening, say theta is 0, let us just give an example, this is alpha here, this is a minus alpha here, like that it goes. So what I am going to do, I am going to plot here this value, this block, which is going to be a measure of half a square omega, here I wrote alpha divided by d omega. D alpha of course remains this thing. You can also say d alpha, let me also put it this just for the sake of. So this is what I am going to put. See earlier I did not have this, what earlier I did, I put half a square omega divided by d omega. Here I have to put this, because remember the overall volume, now the volume under this should become the energy. So this is what we mean by describing short crested C. Okay. Now That means it has got a dependence on omega and on theta. Now let us look at some physical reality part. Okay. So this we understand this we are plotting it. Now let us say from all which direction the wave comes in. Now I am going to plot in this way theta again, because we have to keep on plotting that. So I call this easier to see, this is the omega, see this is omega axis and this angle is the theta. Now you see here what I am saying, I have all the waves coming from this, let us put it this way. I assume that at this point what I measured is all the waves coming this side, then all the waves coming this side, then all the waves coming this side, then all the waves coming this side. So what I am saying is, see that the measured data consists of all the waves coming from all sides, but now there is a problem. You see here, take this opposite, all the waves coming from this side and this side. What would happen if they are same frequency? They would cause a standing wave, but however we have a progressive wave. So what happens is that is very important, we have to say that all the waves that is coming are only over one half sector, because the other half sector is exactly opposite, and if I consider them I end up getting a standing wave. Or if it is a different frequency, see if I use this as A1, this as A2, I will end up getting a standing wave or a part progressive in one side. So what happens therefore from physical, you can easily understand from physical point of view, I will have to presume this integration, that means if I were to call eta to be an integration over d theta over d omega of a omega theta, cos k x cos theta plus y sin theta minus omega t plus beta, something like that. Okay. If the graph was, you understand this is only a integral form of the equation. Instead of writing that, I said summation is integrated from a omega theta this, but over d omega d theta, and here it was 0 to infinity and here it was 0 to 2 pi. But now we see that this should be actually 1/2. So 1/2 means 0 to pi, or it is easier to write in terms of minus pi by 2 to plus pi by 2, because that gives you a dominant direction and spread both sides. See 0 to 2 pi is a question of opinion from which you call 0. Okay. 0 to 2 pi means I call this wave all the way this much. Now here I am saying the waves will be only over this one of the half sector. So I can call this, see if I call 0 to 2 pi from here I am calling, but if I call this way, then I have got basically minus pi by 2 to plus pi by 2. The question what I am saying is that whether you call 0 to pi or pi to 2 pi or like minus pi by 2 to plus pi by 2 is the same thing, because you are talking of waves coming over in a half signal. So it is a more convention to use, physically also more I will tell you more easier to visualize to use minus pi by 2 to plus pi by 2. Why? Because remember waves are created because of winds, primarily these are wind driven waves, wind generated waves. So wind is going to blow in some direction, wind, and you would expect most waves to be in that direction, but we are saying that this wave can be actually from 90 degree plus minus, means 180 degree. Obviously this will be the primary, and you will think waves coming also from somewhere this direction and also up to this direction. So if I take this as base, then the waves become minus pi by 2 to plus pi by 2. Rather I would have a most dominant very high kind of wave at the direction the wind blows, there will be other waves coming both sides 90 degree split. That is more logical. After all, I am only looking at the integration. So if I do, for example, 0 to minus pi by 2 and 0 to plus pi by 2, with 0 is the direction of the wind, then it makes more physical sense, and of course it satisfies my property also. So we typically this is done. Okay. So therefore what we are saying, we say that I can model, once again coming back to this irregular wave, I can model this irregular wave by summing or taking waves from all directions, but now I find out that the directions I need to take only over 1/2 of the full circle, that I can write more easily from minus pi by 2 to plus pi by 2 in an integral sense.
So, but this is done with the assumption that the waves coming from different directions might be of the same omega for them to create a standing wave.
Yeah, no, even otherwise, see, even otherwise, the point is that if no, same omega, because after all what is happening that when you are considering integral, for each omega there is an omega there. There is an omega for each omega. So, if you take each omega and each omega, there will be a standing wave. So, therefore, I cannot have, because we are looking at a propagating wave. So, therefore, what we are doing is that we do not have that. Or if you want you can say you have that with amplitude 0. So, the dominant waves are all coming from basically within this half sec, that is what we are saying. That makes more sense in the modeling part. Okay. Now comes the question of spectrum. Well, we have seen that obviously the spectrum you have to plot this part. We need to plot so called what I just now I showed in a diagram. We showed that we are plotting this height, right, d omega d theta etc. But how do I now model it? See, now I have a modeling question. I really do not know how it has spread. After all, when I get a signal like this, I can make a Fourier analysis, and Fourier analysis allows me only my frequency distribution, but I cannot have the spreading distribution, theta distribution. I cannot get that information. See, if I give you a signal, I tell you to do FFT, I can find A omega versus omega. But here I am making that there is also theta there, that I cannot get from FFT for signal processing. We must understand this. So, then what happened? I have to make a model of it. Now comes the question of this model. Now, you see, same wave, it goes like that. Again, we will get back to the same wave. Now, person A made it a 2D model. So, he has a formula for S omega 2D versus omega. He has this, person A has made this and has a formula for that. It looks like this, omega versus S omega. Now, same signal is analyzed by person B, and he wants to write this in terms of a kind of a like a omega theta omega. He wants to write it as 3D omega theta versus omega and theta. If you want to plot, you will obviously end up plotting that. Now, the same signal, remember. So, what is happening? One interesting point is obviously what is happening is that, see, energy under this wave is S 2D omega d omega. This is my energy of the wave 0 to infinity, and energy under this wave, this signal in this model is going to be but these two must be same, because they represent the same energy, total energy. After all, energy cannot change, it is a question of viewing it. The same waves, I am thinking person A thought, well, I am going to model it by saying it is coming out from direction 1. Person B says, no, I am going to think it is coming from direction 1, direction 2, direction 3, etc., etc. Energy remains same, area under that will remain same as volume under this. So, I have this fundamental relation, that is area under S2D. If I will to write it again, that is, if I were to write this in S2D omega d omega must be same as so here comes the question of modeling. What is done is that people model this S3D. This is a very important assumption. This is assumed as, first of all, it is assumed that it can be broken down to two part, F1 this thing and F2 theta, as if, see, this is an assumption, you presume that I can break it down to this a part purely function of omega and a part purely function of theta, and now this part is taken to be S2d omega and we call it f theta. So, it is presumed therefore, see this is very important, that a 3D spectrum can be written down as a 2D spectrum multiplied by a function which is function of theta alone. This is known as spreading you can easily know why it is spreading function, because what we have done, we have taken S2d. See, if I were to now look at this side, this is my omega, I have done S2d part here and I simply spread it this side, this is theta side, by a function, multiply that with a function and go down, taper it down. That gives me spreading. See, for example, if f theta was 1, then it will be equally spread, means there is an equal chance of all waves coming from all directions. But we know from physics that wind is blowing one side and you expect most waves in that side and only a small waves on other side, and as you go 90 degree of the wind you expect very less waves coming up. So, wind is blowing in, suppose wind blows this side, you expect most waves at this side and very waves coming this side, very less wave. I mean mostly see 80% here, maybe little less on coming from 45 degree, even less from 30 degree, practically nothing from 90 degree, sorry 45, 60, 90 like that. So, this obviously it is always spread, it is supposed to have this theta is supposed to have this, if I were to plot 0 to pi by 2 or here minus pi by 2, you expect this spreading to have a bell shape. That makes sense, isn't it, because this tells me the strength of the wave coming in direction 0, wind direction, and obviously the strength will reduce, the percentage of waves coming from direction away from 0 would be less as you go farther from 0. It is spread. This idea we must get in your mind. Once again I will tell you the spreading function concept. So, if I were to put theta here, if I were to put f theta, you would expect it to, first of all f theta will be 0 beyond minus pi by 2 or plus pi by 2. So, if I call this plus pi by 2 minus pi by 2, you will expect it to be maximum here, 0 here, and it will be something like that. That is a excuse me, that is a realistic model. Of course, you cannot say why not that. Well, we can always do that. People have also analyzed the spreading function somewhat by taking the wave slope. You know, actually, although I say you cannot measure, but you could measure nowadays with sophisticated instrumentation from a random signal the slope also. After all, if it is all going in x direction, I have a slope in one direction. If it is coming from this direction, I have slope in different direction. So, if I measure the slope, I get a feel the content of excuse me again, content of directional waves. So, people have been doing, obviously it is found most waves are in the direction of the wind. So, this is what we do. Now comes the question of how do I model it. So, we look back to this equation again and we go back to this. Now I find out this, let us write in another paper. So, I have S3d omega theta is equal to S2d omega f theta. The other next come the question, well I am going to put it here. Now, integration over that d omega d theta is same as integration over that right, I mean the integration over that this. Now, this see carefully follow, area under that is S3d this d omega d theta, but S3d is written as S2d omega and f theta d theta, f theta. So, when you integrate that, it will be between the omega and between this theta. This is just from identity, from the approximation we used, because we said this is this into this. Now, however, understand that this side is also same as S2d omega d omega. This side same as this, because we found the area is same. So, if this is same as this, what do I get? I say I get that minus pi by 2 to pi by 2, right, must be equal to 1. So, what we end up getting is that we say f theta is a model. I can use any formula, but don't you must use a formula for f theta, so that this condition is satisfied. This is very important for us to understand. We must have this condition satisfied. F theta d theta must be equal to 1 over this. So, this is a spreading function, and we must have this relation. Now, what can be the possible spreading function? Well, as you understand, since it is not fully clear, people have modeled the spreading function many ways. Most usual way of modeling is to use a cos theta graph. The y cos theta graph, you see, if you use cos theta, a cos theta, here it is pi by 2, here it is 0, cos theta basically goes like that. Cos theta has this look, no, that it is 0 maximum at 0 and at pi by 2, maximum value at theta equal to 0, and at theta pi by 2 it is 0. So, it has got this kind of a spread. So, essentially f theta, people, it would obviously you cannot use sin theta as a model, because sin theta would be exactly opposite. You would want to have cos theta, the f theta, remember I wanted to have f theta which is maximum here, and as you go down, lowering down. This is one possible way, but people do not model that. There is a problem of using cos theta alone. Why? Because you see here, you know, it is like this, the graph, or maybe it is like this, but what you want is actually like this, because so that it comes down tapering, and this can be done by using cos square theta or power of cos theta. So, typically you will find out now that 2 by pi is a possible function that will actually look like this, and it also has an interesting property that the slope becomes 0 here. The function, maybe we should put potty name, it becomes like that. It goes to 0 if I use this, okay, forget this, just cos square theta you take. If I take cos square theta, it will go to actually maximum here, go down to 0 here, as well as the slope is 0 here. But then of course, if you use cos square theta, the integration is not 1. So, therefore, you have a constant coming 2 by pi. Now, from this analogy we can find out that there can be f theta of the form which will look like co, where you can have different m you can find out. Of course, you will find out that larger the m, more picky it is m, as m goes up. See, as what I mean, if you use cos square theta, that of course there is a constant 2 by pi. If you use cos 4 theta, it will be some other constant, because obviously the area under that has to be 1, as I said. It may be, in fact it may be something like 8 by 3 pi, that can be worked out. But my point of view of saying is that as you use more power, then you have got pickier. What does a pickier means? Obviously it means there is less and less spread. So, you know, if you use, now here is a question of modeling. Let us say that you went to North Atlantic, you find that, well, there is a 3-dimensional wave, all right, but majority of the wave is much more in one direction, much less in spread. So, you would use a function, choose a function from literature which is a higher power of cos, more focused. In fact, larger the m, we call more focused the waves, because it is more in one direction. Smaller the m, more spread. cos square, the lowest one that is used is typically 2 by pi cos square normally. We do not use anything lower than that. Once again the spread is something like spread, you know, like how much the directional content is there, and it is very illogical to think that waves from all direction are of same probability. Cos, say it again.
Any power of cos is always an even function, so we don't have to take it from minus pi by 2 to
No, no, you do not have to. So, see, minus pi by 2 to plus pi by 2 we are taking because we have actually chosen. See, what we are doing is, I will tell you what we will write this way. It is this. I will answer your question for minus pi by 2 equal to 0 else. Now, the question is actually why we took minus. It is not question of functions value of theta. What we chose is that we said from physical ground I can use from any 0 to 2 pi, pi, as long as I use what you say is correct, as long as I use from 0 to pi some one unit, it will become same thing. Question is what to take. So, it satisfies us or easier to visualize if I took minus pi by 2 to plus pi by 2, because what would happen, then I can think that 0 is my dominant wave direction and I am spreading. If I take 0 to pi, you know, like pi, then I have to think my dominant wave direction is pi by 2. I can always take from in fact alpha minus pi by 2 to alpha plus pi by 2, okay, and make alpha anything you want, 360 degree, then you will take 182, you know, like 4 whatever. But we do not want to do it, because one thing, you know, that we should not unnecessarily complicate things. Why we have chose always x wave direction, because it is easier to think that way. So, that is the reason why you can choose anywhere, does not matter. What your question is only with a reference point. If I choose the reference point as 90 degree dominant, then I have 0 to 180 degree. If I use 270 degree dominant, I have 180 to 360 degree. So, should you use 270 or 180 as dominant direction? Rather, it is better to use a 0 degree dominant direction. That is what we are doing. Okay, so this is how it is. So, this is how the spreading goes here. And now, what is happening is that if I were to draw this, you know, like spectrum, there several people draw in several ways. If I were to draw in a theta direction, rather, it is difficult for me to plot this. So, this angle is theta. So, what would happen? It is something like this graph. You are kind of rotating this graph, both sides and pulling it down. That is what you are doing, right, because theta is this, see, this is theta. So, you are essentially this graph, you know, this graph, you are rotating it this and pulling it down. See, if I were to look at this way, rotating it and pulling it down, both sides. As you go to 90, it becomes 0. So, this amount it is coming down is f theta. So, this is one way of. So, if you look at that, you are going to get some picture, you will find a picture will looking like that, you know, a kind of shape will come like that. Not really it does not look like a conical shape, because question of the way you are looking. And if you were to draw in terms of this as theta, this is omega, you will find out this thing coming down to 0 as you go less. In fact, lot of plots have been made in actual literature of directional content. They will look something like this, you know, I tell you, the picture will look something like, you know, there is some bar chart there. It is difficult to plot here, but it is going to make lot of spikes over this domain, certain domain, because not all waves of all comes, certain omega and certain theta. If you were to measure, it comes out like a cluster, like a bell shape. People have done it, measure, as I said, nowadays it is becoming fairly sophisticated to also be able to determine directional content from what is known as wave slope. We have, say, ocean satellites, they are collecting whole lot of ocean data. They collect, besides wave heights, nowadays they are also collecting slopes. Similarly, the data buoys are there, they keep collecting slopes. So, long back it was only wave height, but now you also have slopes coming in, and from there directional content has been worked out many times. So, they look like that. So, this is what is a 3D spectrum. Now, of course, having said 3D spectrum, now suppose I have got the spectrum now. So, you see opposite now we see how do I reconstruct the signal. So, I have this spectrum S 3D omega theta. So, I want to find out what is eta t. Okay. So, like some people will want to find out what is eta t. What we can do of course is that this is given by straightforward A let me put it k here, the I. Omega I. This will be a random value. So, what you have to do is that you will obtain this by I equal to something 1 to n. So, what is happening? You can reconstruct this way, and where A omega I theta j will be given by 2 S 3D see earlier what is happening, if you remember, this is why I said this is that here the question is like that I have this formula given, after all this formula is known to me now. So, I have this formula given, I can find out this, reconstruct a realistic realization of the ocean wave, reconstruct what should be the eta t, means reverse problem. I have a spectrum here, see in a 2D case I have the spectrum here, find out what would be go from here to there. Where do we use it? What is the use of this kind of information? Very useful, because think of this, I have a ship, I have to find out what is this realistic like realization. Now, somebody tells me, okay, use C spectrum by this formula. Now, I go to use the C spectrum. He says take C state 4. So, I know this formula. So, I have this given to me. This is given to me, but I want to know this means physically what kind of waves. Let us talk of tank, wave tank. I want to make a model study. I cannot feed this. What do I feed? I have to feed this. After all, in a tank I have to create waves which will be like this. What is this? This should be such that it is statistically equivalent to this. So, I must have to create a real time signal. Remember, this is a real time signal in real time. So, if I want a 2D spectrum, I have to create real time spectrum. Let us say that you are doing a model test for a ship or for an offshore structure in C state 3. So, I have to send the waves which is same as C state 3. What do I send? Well, I have a tank here, I have a wave maker here which oscillates this way. As it oscillates, it creates waves. So, this is S and this is eta. So, I actually eta by S defined, typically you push it 2 centimeter in this frequency, you are going to get this height, etc. So, the question is that I want to create this. This is my place where I am going to put my structure. So, I want to create a realistic wave. I want to test this structure in C state 3. So, I go to formula, I end up getting this spectrum, but this spectrum I cannot feed. I have to break it down to this signal and then only get the signal feed, and of course I will get back a signal out similar which I have to reconstruct back to this. After all, reality is in real time, there is no imaginary, no frequency domain, etc. So, what is happening, I require to create this. So, what I said for 2D spectrum, I created that by simply saying eta t was equal to 2 S2D. Well, let me put it the other way around, A omega I cos k I x minus omega I t plus say some beta or theta, say beta, we call it beta I. So, you see here, and A, the omega I was given as square root of 2 S 2 D omega I d omega. This is how we have got it, right. If you have a doubt, what we have done is, well, here what we have done is something like this, you see, this one, what is this, S 2 D omega, this omega I, let us say d omega equal to half A omega I square, A, well, we can call it A omega is A I equal to square root of 2 S 2 D d omega at this omega I, you know. Okay. So, therefore, I end up getting this eta by summing this all. So, what I mean, for each one I find out what is, for I break it down to several parts, for each one I find out what is the amplitude of the wave of this frequency, add them up with a random phase. Here what I have to do in a 3D case, I have to do the same thing, but I have to do a larger breaking. I have to break not only over the I axis, but also over the j axis. So, what I am saying therefore is that, see, it is, this is you will understand this. So, if I take the same 2D spectrum of say height, let us say height equal to 5 meter, I will end up getting a maybe wave like that. Now, if I use a 3D spectrum, what I will probably find out is a slightly more randomness, in the sense that this might have much larger number of waves of one particular frequency, like typical, or rather if I were to use an extreme example, a 2D might give something like, say, more like this in a very special case. 3D is going to give me slightly more spread, somewhere small, somewhere bigger, etc. In other words, this will have much more focus omegas, because all are in one direction. This one will be a little more spread, you see. So, anyhow, this is only a qualitative assessment. The question therefore, you see here, that when I talk about experiment, now I have this interesting point. I have this tank, I have to create this wave. So, what we do, you know, we break it down to this signal, then I break it down to the feed I have to give to this wave maker, and I give that. See, in order to get this, I have to find out what is the corresponding this S value, and that I give it to here, I push it that way. So, now see, if I want to make a 2D spectrum, I simply give this signal. If I want to give a 3D spectrum, I will give this signal. So, as far as the tank is concerned, I can make actually of course, in the 3D spectrum in a tank I cannot really make in a long tank, that's not correct, because in a long, because the point is that there we are making all the wave in one direction. In fact, that's I have to correct that. Well, we can create this way the spectrum time signal, but however, I really cannot create waves in a long tank use a 3D spectrum, because in this case I am actually sending waves in all one direction. Actually, for this purpose only I need a so called, you know, like wave basin, which looks like that. I will just spend this little time. You will have a wave like IIT Madras has got wave basin like that, where we have got this wave maker this side. Earlier days people used to send waves this side and wave this side, and then combining you could get. Nowadays very interesting phenomena is there, you can actually have multiple segment of wave maker. If you move them like a snake type, if you move this one here, this one here, this one here, etc., you will find out you can make directional wave. How you know? It's I will also tell you this. Suppose I move this more, the crest would have come here. This is slightly less, the crest would have come here. This is slightly less, the crest. So you end up getting a wave like that. So what happened? It's very complicated theory, but you can move this wave maker like a snake type. Like when it is here, next one is here, next one is here, like that, and then you can make directional wave. Very complicated, but you can make. But having said that, so what we have understood, I want to just spend this time on this class on 3D spectrum only. See, what I understood is that I have 2D spectrum, I have 3D spectrum. 3D seems to be more realistic. Okay. After all, when you go to ocean, you say it's 3D. Why the hell do we use 2D spectrum? What is the use of 2D spectrum then? Somebody may ask the question. Why I spend so many times how to find out the response in 2D spectrum? Now there is a good reason for it. You see, as I said, in 2D spectrum I am presuming all the waves coming from one direction. So therefore you would expect it is much more, all are focused in one direction, and suppose I have a ship which responds much heavily for wave coming in one direction, then it is going to go up and down much more. Now same wave, if I same ship for same wave height, if I assume come from all direction, this is going to be slightly mellowed in this direction. See, then what will happen? Extreme example, single wave. Suppose this whole thing is modeled by one wave of 5 meter height. So in 2D case there is a wave coming of 5 meter height this side. 3D case I will say there is a wave of 4 meter height this side, 1 meter height from other side. Now this body seems to respond mostly for wave in this direction. So in the case 1, the 2D case, I end up getting usually a larger response, larger heave for example, or large, in the case of beam larger roll. Now therefore if a ship is designed which can survive 2D spectrum, it would normally be lesser in 3D spectrum. So therefore if you could actually, after all you are going to design the ship for 2D spectrum coming from all direction. So if I could make the ship survive a 2D spectrum from all direction, then I would more or less think that that would be more than sufficient for it to survive a 3D spectrum. This is a one of the reason why 2D spectrum, despite its assumption, is still valid, is still used for all my actual calculation. Otherwise we would not have done it. We would not have used at all 2D spectrum, but even now it is used. Now tomorrow's class we will find out the response in 3D spectrum, which is you are going to find out it is nothing but one more level of algebra. See, here I have added all the omegas and responses in omega direction. There I have to repeat that in theta direction. So here I have one piece of paper with omega and this thing. Here I have to do each piece of paper for one theta, 10 pieces, and add them together. It's just one level of algebra. So there is nothing thinking involved in that. It is only a level of algebra involved. But still, having said 2D is useful, because 2D gives me usually a large, usually but not always, a larger response, a more conservative kind of a design comes out of that.